In the last 3 lectures, I described the construction of superstring field theory. Okay, so these lectures are supposed to be on the applications. Okay, so today I'll be somewhere in between. I'll try, first briefly review the construction of the string field theory, and then I'll do something which is in between real applications and formalism, okay, which is to derive certain word identities. Okay, but the applications of those word identities will become clear only later. Okay. So we introduce the string field. And we saw that it has 2 components, okay, which are denoted by psi and psi tilde. Psi was an element of h hat t, which is h minus 1 plus h minus half. I'll explain these notations again. Okay. So this is in the heterotic string. Okay, just for convenience, I'll focus on heterotic string. Type 2 will be similar. And psi tilde belongs to h tilde t, which is h minus 1 plus h minus 3 half. And the definition of HP was picture number p states in world sheet superconformal field theory, okay, satisfying B0 minus on S equal to 0 equal to L0 minus on S for S belonging to HP. Okay, so these are all picture number p states, but subject to these restrictions. Okay, where the notation was B0 plus minus was half B0 plus minus B0 bar, L0 plus minus, sorry, not half here, was L0 plus minus L0 bar, and he also introduced C0 plus minus, which is half C0 plus minus C0 bar. So this means that both psi and psi tilde are infinite component fields, okay, because these are of course Hilbert space of superconformal field theories, which is infinite dimensional. One thing I didn't mention last time, but let me do it now, which is the psi and psi tilde, okay, are Grassmann even. Which means that when expanded in a basis, the coefficients are even or odd if basis state is even or odd. Okay, so if you write psi as sum over r psi r phi r, where psi r are the coefficients and the phi r are the basis states, then if phi r is even, then psi r is even. If phi r is odd, then psi r is odd, which makes psi always Grassmann even. And the same is true for psi tilde. Then in terms of these, we wrote down the BV master action of string field theory, which is the structure Okay, so here GS was the string coupling. Okay. This was BRST charge. G was identity in the NS sector, which basically in our context corresponds to H minus 1, and this was chi 0, which is integral dw over w chi of w in the Raman sector, which is H minus half, H minus 3 half, okay. And chi is the picture changing operator. Okay. And finally, this symbol for any set of states, say A1 to An, okay, these will belong to typically H hat T, which is here. We wrote down the expression for this. Okay, if you don't remember what it is, it doesn't matter that much. Okay, so this is some correlation function on a genus G Riemann surface on, well, let me put this sum over G, Gs to the 2G. This is some correlation function on a genus G Riemann surface with vertex operators A1, A2 up to An. Okay. These are in general off-shell states, okay, and there is a very specific way you have to define these correlation functions. And the important point is that this R bar GMN involves integration over a subspace of the moduli space of Riemann surface, and this subspace doesn't contain any degenerate Riemann surface. Okay, so this is completely well defined. Okay, it has no divergence from the boundary of the moduli space. Okay, because this subspace doesn't go anywhere near the boundary. Okay, that's the important point. So this gives a concrete definition of what the string field theory action is. Okay, without running into any divergence. Are there any questions on this? And then at the end of last lecture, I mentioned an identity. Okay, I think this was probably half of the people had already gone away by then. Okay, so let me write down the identity again. That's this. This is the identity that is satisfied by this product. Okay, this will in fact be one of the key identities that we'll be using a lot. So I'll try to explain this in some detail. Okay, so first let me explain what these phi r's are. Okay. So phi r, okay, is a basis state in H hat T, okay, and phi RC is a basis in H tilde T. Okay. So H hat T and H tilde T, as defined there, are conjugate spaces because inner product pairs them. the BPZ inner product pairs them. So these are basis states in H hat T and H tilde T, okay, and they are normalized so that phi RC C naught minus phi S is delta RS and phi S C naught minus phi RC is delta RS. Okay. And this sum over here, okay, is a sum over all possible ways to partition this 1 to n into two subsets. Okay, you see that you have a subset I1 to IL level by I1 to IL, a subset level by J1 to JK. Okay, so you take this set 1 to n, divide them in all possible ways, okay, and you have to sum over all possible ways of this division, okay, and of course there is a sum over R and S is understood, okay, because those are repeated indices. Okay. So let me say a few words about where this identity comes from. Okay. The left hand side, okay, to evaluate the left hand side you substitute here A1, replace 1 by QBAI, okay, and you sum over I. Okay. That, as you had seen, is a total derivative, right? Because omega satisfies that identity which lets you express whatever will appear as in the integrator on the left hand side, okay, as d of another omega. Okay. So because it's d of another omega, the result will be an integral over the boundary of R bar GMN. Okay. R bar GMN is a sub-region of the moduli space, okay, and you have to look at where its boundaries are. Okay. And those boundary contributions are precisely what you see here. Okay, so that's the way this identity is derived. Okay, we express, you use the identity for omega, that omega of QB of A, okay, where QB acts one in turn on each of these, is d of omega, okay, and then you express the integral over the boundary and evaluate it. Okay. Again, the important point is that these boundaries, because R bar never reaches degeneration points, these boundaries are perfectly well-defined objects, right? These have no degeneration, no infinities. Okay, these are perfectly finite contribution, and here they are. Okay. And I also mentioned that it's using this identity, okay, which is one of the key identity, okay, that one can show that the action that we have here, okay, satisfies the BV master equation. Okay, I'll not write down what the master equation is because we will work in a slightly different formalism. Okay, but this is what, that identity is what goes in showing that this satisfies BV master equation. Okay, which is a statement that this is a gauge invariant action. Are in? PGM. Yeah, these are integrals over PGM and the fiber bundle. Yeah, yes.
Is there a way to think about it just from beginning modulized?
Well, you can accept that then it will, you also have the point is these quantities depend not just on the moduli space but also on the choice of local coordinates, right? So then you have to put those as extra explicit data, right? It's easiest to think of them as integrals over PGMN, right? Which already encodes the local coordinates, right? Which are encoded in the definition, right? So the whole string field theory action that you construct depends on a choice of local coordinates. But as I mentioned, that dependence one can show can be removed by field definition. That different choice of local coordinates or picture changing operator locations give different looking string field theories, but they are all related to each other by field definition, and hence the final physical answers don't depend on them. Okay, but at the intermediate stage you do have the dependence, and that's why it's easiest to think of these as integrals over PGMN, the fiber bundle. Okay, so what we are going to do today is to derive word identities from this action, okay, and those identities, okay, and see what kind of word identities we can derive. Okay. There is one more point perhaps I have to mention, okay, which is that we can gauge fix that action using Siegel gauge. Which is simply that B naught plus psi equal to 0, B naught plus psi tilde equal to 0. Okay. And in this gauge, we got the propagator as okay. In fact, we got the propagator first and then reworked out. Then worked out what the corresponding kinetic term is. Okay. So from now on, okay, if we want, we can just forget about the Riemann surface completely. Okay. And everything that we do can be done simply in terms of this action and that identity. Okay, but of course, it's often useful to go back to the Riemann surface picture and see the interpretation, but you never have to go back to the Riemann surface picture if you don't want to. Okay, you can just work with this action and that identity. So first identity that we will be deriving is the same one that we derived earlier based on the Riemann surface picture. Okay, but now we will see that the possible boundary contributions that we had worried about, okay, will be automatically absent. Okay, will not matter once we use this action and those identities. Okay, so what is this? This is the full off-shell Green's function. This is full off-shell Green's function of A1 to An with external tree-level propagators truncated. Okay, this in fact is what you normally calculate using Polyakov amplitude or generalization of Polyakov amplitude using off-shell external states. So this is given by sum of Feynman diagrams. Okay. Now first you have to worry whether this is a well-defined object. Okay. Whether when you express this as sum of Feynman diagrams, can there be divergences? Okay. And the answer is indeed there can be divergence if there are massless tadpoles. Okay. So for example, okay, now let me first explain what I mean by external legs truncated. Okay. So what I mean by here, okay, that the external propagator is truncated, that if you draw a diagram like this, okay, you don't include the propagators correspond to these lines. Okay, that's often what is used, and in the LSD formalism we know that we have to truncate the propagators. The difference is that in the LSD formalism we have to truncate the full external propagator. Okay. Here you are just truncating the external tree-level propagator. For example, if you have a graph like this, okay, you will remove this, okay, but you will still include the rest of the diagram. Okay, so this is not, eventually this is not what you will use to calculate S matrix. Okay, nevertheless this is a very useful thing to illustrate the how to derive odd identities. Okay, particularly because what you calculate in string theory is this. Okay, and that's how you get these divergences. Okay, so let's look at a diagram of this form. Okay, and suppose you are trying to calculate this in string field theory. Okay. This leg has a propagator which is 1 over k square plus m square, okay, which is okay as long as m is non-zero. Okay. See, this leg the propagator is this, but k is 0 because by momentum conservation k cannot flow anywhere. Okay, so k is 0. So this diverges for massless tadpoles if there exist massless tadpoles. Okay, so if there is a massless field with a non-one-point function, then this is divergent. So what I am going to do with this G doesn't make sense in that case. Okay. But for now, proceed assuming no massless dipole. Later on, we'll rectify this. Okay. In fact, one of the motivations for doing string field theory, of course, is to deal with these cases. Okay, when you have massless dipoles. And this in the Riemann surface picture will show up as divergence. Okay, from the boundary to the moduli space. The second point I want to emphasize is that this doesn't have an on-shell limit. G, the on-shell limit is divergent. The on-shell limit, of course, is precisely Polyakov amplitude. Okay, and the fact that it is divergent is why we are doing string field theory. So let me explain why on-shell limit is divergent. Okay, it's divergent because G includes diagrams like this. Okay, you truncate the external propagator, so these are not included. Okay, but this line, which is 1 over k square plus m square, okay, when this leg, okay, is the same as this leg, okay, this is on shell, so you'll get 1 over k square plus m square evaluated at k square plus m square equal to 0. Okay, so it will diverge. Okay, so G is again, it doesn't have an on shell limit. Okay, and again that is the reason why you are doing string field theory. But for now, let's proceed with G, and we avoid this problem by simply working with off-shell external states. Okay, for off-shell states, of course, there is a problem, right? Because for off-shell states, k square plus m square is not 0. Now I'm going to write down the word identity on this side, but let me first see what we want to calculate. So what we want to calculate is this object, sum over I okay, the result of applying QB one at a time on each of the external legs. Okay, the same as this, except that now you are talking about the full amplitude. So how do you calculate this? Okay, G, of course, is a sum of Feynman diagrams. There are many Feynman diagrams that you can draw for G. Okay. You are applying QB on each external leg one at a time and summing. Okay. So the way we analyze this is that we take any given vortex, okay, and pretend as if you are applying Q not only on the external legs but also on the internal legs. Okay. Then we are doing adding something extra which have to be subtracted at the end. Okay, but let's suppose that we apply Q on each of the external legs as well as on the internal legs. Okay. In which case we can apply this identity because the vortices are just this. Right? Each vortex is just this curly bracket. Okay, so you can apply this identity, okay, to simplify it. So I'll write down the result. I hope this is visible. I'm going to erase this because I need this space for writing down the identity for G. The first two terms are minus sum over G. So basically what happens is that you replace whatever identity was there for gamma, for that curly bracket, okay, you replace those by G, okay, because effectively you apply the identity here, okay, it gives you a gamma on this side, a gamma on this side, okay, which combines with the rest of the diagram to give part of the contribution to G, okay, and part of the contribution to G here. Okay. So these two come from applying the QB on each of the lines coming from each vertex. Okay, you take every vertex and every line coming out of the vertex and you get those two terms. Is this clear? Okay, for example, suppose you have something like this. Okay, suppose you apply the identity here. Okay, so effectively these vertex, okay, will split up. Well, here is not very useful. Let me draw a four-point vertex. I think four-point vertex is the, let's suppose we draw it here. Okay, and you apply the identity here. Okay. So there will be contribution of the form where this line that I have drawn, okay, is basically separating the 4 into a subset of 2. This goes on one side, this goes on the other side. That's this operation. So the dotted line is this operation over here. Okay, so every vertex you replace by the dotted line, which is this operation. Okay, and you can easily check that after when you do this for every vertex of every diagram, okay, at the end what you are left with is a G, okay, or two G's with two vertices connected by the dotted line, which are these. Okay, so this, for example, will be a particular contribution to the second term. Right? It's a single G, two of its lines have been connected. Okay, on the other hand, if you have, for example, a diagram like this, suppose you have a 4-point vertex like this, okay, then this splits into, when you apply QB on each of these external lines, okay, and apply the identity for gamma, it will split up into this, and this is one of the contributions to the first term. Okay, a G times a G. But this, of course, is not the full contribution, because you have to now worry about the fact that we have overcounted the application of Q, right? You have applied Q on the internal legs, which you shouldn't have done. Okay, so you have to subtract off that contribution. Okay. So let me write down the result for that subtraction, and then I'll try to explain briefly where it comes from. Yes.
There was a half there, so in the identity.
Okay, yeah, I can, yeah, this half is still there. See, this is basically a symmetry factor, right? That when you have two legs, right, you could either do it this way or that way. So if you just work out a combinatoric factor, that's where the half factor comes from in gamma.
Again, explain this way of splitting the lines.
Yeah, so suppose you have this vortex, right? You apply QB on each of these lines, right? And then you apply the corresponding identity for gamma, right? This is a gamma, right? And I'm representing this factor by the dotted line, right? So it's a sum of all possible splittings of this vortex into various legs. So this is one possible splitting, right? So this is one particular contribution that comes from gamma, right? And this can be identified as some of the part of the contribution to G.
I guess maybe the confusion is G was, your early identity was general for a general endpoint.
Yes.
Function. But this is for these external, Green's functions with
specific external states, A1, A2 up to N.
But at each vertex, when you apply, it's not necessarily a Green's function that appears. Right?
This is a vortex, this is the curly bracket.
So you're applying the identity to the curly bracket?
Yeah, so that was.
Not this side, not.
No, this is what you want to prove. See, I'm going to evaluate the left hand side, right? The right hand side is what I'm evaluating now, right? So left hand side, I'm using the fact that G is built from the vortices and propagators, right? Sum of Feynman diagrams. So now, left hand side means that I'm applying QB one in turn on each of these lines, right? That doesn't give something simple, so I now add many new contributions where we apply Q also on each internal line at the two ends. Okay. Then for every vortex we have sum over QB on each of the external lines. Right. Every vortex is a curly bracket. Right. I'm now applying the identity that we derived for the curly bracket. Right. And that's what gives this split. Right. Applying that identity on this.
So it's the curly bracket identity?
That is a fundamental. That's what I'm using to derive the identity for G.
How is the second line represented by diagrams?
Oh, second line, see this is a contribution actually to the second line. Okay. This came from the point of view of the curly bracket, this came from the first term. Okay. But because of the specific structure of the Feynman diagram, right, it's still a connected Green's function, right? So this is actually part of the contribution of the second line, right? Because you have a G, okay, with two vortices attached. Okay, this one, okay, will be a contribution to the first line. Okay. So it's not that the first line of gamma contributes only to the first line of gamma and the second line contributes only to the second line. They can get mixed up. Okay. But eventually, if you shift through all possible terms, you will find that each diagram is represented on the right hand side.
And then rotation phi r phi s being separated by the colon. Semicolon means that phi r phi s need not be on shell.
No, nothing is on shell. This is fully off shell.
And I mean, it doesn't have this external legs, not on shell, I meant this external legs truncated.
Yeah, the extra phi for phi or phi is, of course, those are the internal propagators, right?
Exactly. So
yeah.
That's why that is those two are on different.
No, inside G, they are on the same footing. Because the propagator, see, there is the propagators are all inside G, right? So phi or phi is, when you split like this, for example, right? There is no external, there is no propagator here.
Okay, so you don't, so that's the Green's function, but without any.
Exactly, yeah.
So
okay.
It's as if just, it's sort of.
It's as if there's truncated Green's function, right? Yeah, exactly. So this part, if you just remove the dotted line, it's another truncated Green's function. Okay, the other thing I perhaps should have mentioned is that the AIs, okay, are not necessarily in the Siegel gauge. We are using the Siegel gauge for the internal propagators, but as far as the external lines are concerned, you can take them to be arbitrary elements of H hat T and H hat T, not imposing Siegel gauge condition. Okay, so let me write down these two terms and then I'll explain where they come from. Okay. So this term, okay, comes from the following fact that take this diagram for example. Okay. So here, okay, we have added some extra terms where QB acts on this and QB acts on this, right? We have to subtract this off, right? So there will be QB on one side of the propagator and QB on the other side of the propagator. This is a regular Siegel gauge propagator. Okay. And if you work out the signs correctly, you will find that you get two Green's functions, okay, one on this side, one on that side, and a commutator of QB with the propagator, which is what you see here. Okay. And similarly, when it's one of these lines, suppose you have this line and you have a QB acting here and QB acting there, okay, then again you have QB commutator propagator, which is there, okay, but now it's connecting a single connected Green's function. Okay, so that's the last term over here. Is this clear? Okay, so these are coming from applying the original word identities, and these are coming to compensate for the over application of QB. Okay, and that you are compensating by picking up the commutator of QB with propagator. Okay, the fact that it comes as a commutator is something that you can verify explicitly by keeping track of the signs, and this is what you get for the final word identity. And now it's easy to see that this is 0. This is 0 because QB with this commutator, okay, QB anti-commutator B0 plus is L0 plus. Okay, so that kills this L0 plus inverse, and then you can see that this third term exactly cancels the first term and the fourth term exactly cancels the second term. Okay, so this is 0 using QB B0 plus equal to 0. Okay, and QB, sorry, L0 plus. Okay, and QB B0 minus is 0 in this subspace. Right? QB B0 minus commutator gives you L0 minus, but that of course vanishes on this subspace because on H hat T, L0 minus is 0. Yeah, they actually don't matter too much. If there is C0 minus here, you have a C0 minus, B0 minus, C0 minus, that basically gives you one C0 minus. Right? And any commutator that you have between C0 minus and QB doesn't contribute because then you lose the C0 minus, right? And then this matrix element is 0. Right? So you can pretend as if C0 minus anti-commutes with QB in this subspace, even though it actually doesn't anti-commute with QB. Right? But the very fact that QB C0 minus anti-commutator doesn't have a C0 minus mode, right, makes the corresponding matrix element vanish. Exactly. The zero, you don't have the C0 minus 0 mode in the matrix element, right? And that's how it vanishes. Okay. So this identity is what we had derived earlier, if you remember, right? Just by writing the Green's function as an integral over the full section, okay, not on RGMN. But there we also had this worry that it's 0 up to boundary terms, and we didn't really have much to say about the boundary terms. Okay. What I have done here is to give a proof of the same identity, okay, but now there are no ambiguities involving boundary terms. Okay. The only thing you have to keep in mind that if there are massless tadpoles, then this analysis doesn't work, because if there are massless tadpoles, then G is divergent, right? So then of course the whole analysis has no meaning. Are there questions on this? Now this is important. I went through this in detail because this will be the template. Okay? And once you have understood this, okay, we'll see that the other word identities that I'm going to discuss will just follow as simple consequences of this analysis. So let's then begin with something which is a better defined object, 1 pi amplitude. Okay, which I'll denote by curly bracket a1 to n. This is distinct from the earlier one, the elementary vertices, where we had double brackets. Okay, so this by definition will be the 1 pi amplitude. What is 1 pi amplitude? Is the sum of all one particle irreducible diagrams. Okay, so for example, this is not part of the 1 pi amplitude. Okay, because by cutting this line, it gets divided into two parts. Okay, in fact, none of the diagrams I have drawn here are 1 pi. This is 1 pi. Okay, so one particle irreducible amplitudes, and this curly bracket is just the sum of all such amplitudes. Okay, so and let's see what can we say about this. So we want to calculate sum over I a1 to qb ai to n. So we proceed exactly as that one, okay. Namely that we take every vertex of these 1 pi amplitudes like this one, okay, and pretend that QB applies on all of them. Okay? And by the same logic, we will get these two terms on the right hand side, okay, with G replaced by the 1 pi amplitudes. Okay, this you can easily verify that starting from a 1 pi amplitude, and if you do that, you will always get 1 pi amplitudes. Okay, so these two terms will be identical except that G will be replaced by 1 pi amplitudes, that curly bracket. Now here, there will be a difference. Okay. The difference is that this term, the analog of this term will not be there. Why? Because this term is coming by applying, as we saw, see this term is a product of two amplitudes, right? So where is it coming from? Okay, in the case of G, for example, it was coming from applying QB on one side of this propagator, QB on the other side of this propagator. Okay? You calculate the QB commutator at this and the product of two amplitudes. Okay? But such amplitudes are one particle reducible. They are not included in gamma, in the definition of the curly bracket. Okay? So when you repeat the analysis for the curly bracket, okay, what we will find is that the third term is not present, okay, because all the contribution to a third term comes from one particle reducible graphs.
The last vertex, just the elementary vertex also I thought broke up into.
Yeah, that is the first two terms. It broke up when you applied QB on all of them, right? So this is not from the overcounting, right? Now I am asking about the terms which are obtained from overcounting, which come from internal lines, right? And there this will be absent. Okay. This will be present exactly as it is, except the G will be replaced by the 1 pi amplitude. Is this point clear? Okay. So the result is that earlier, you see G, this one cancelled this one, okay, and this one cancelled this one. Okay. Now this is present, last term is still present, so this will still cancel this one, okay, but there will be nothing to cancel this one. So the identity that the 1 pi amplitude satisfy is simply minus Is this clear? Okay, the first term remains uncancelled, second term gets cancelled by the fourth term. Okay, and the third term is simply not present.
This bracket is 1 pi vertex or 1 pi Green's function?
1 pi Green's function for n external legs. Right? This will be used as 1 pi vertex for the 1 pi effective action. Right? That's what we are going to do now. That we'll use this 1 pi Green's function and then use it as the vertex of the action. Is this clear? So this I want to keep, okay, just if I'm trying to erase it, just protest because I need to use this because all the word identities will be just variations of that. Okay, so I'll not, that way I don't have to write it explicitly. Now, I should add that for the 1 pi amplitude, okay, massless tadpoles are irrelevant. Even if there are massless tadpoles, they are well defined. Okay, because 1 pi amplitudes don't get affected by presence of massless tadpoles, right? Because the diagrams like this, which I just erased, this is not 1 pi, right? By cutting this line, you break the diagram into two parts. Okay, so 1 pi amplitudes don't have contributions of this kind, and hence even if the theory has massless tadpoles, you can still define 1 pi amplitude, and that of course is important because eventually we'll solve the massless tadpole problem using 1 pi amplitudes, yeah, or 1 pi effective action. Okay, so if the action was ill-defined, then you couldn't do what you are going to do. So 1 pi effective action is 1 pi will be and the key point about this action, okay, is that if we now derive the Feynman rules from this action, which means if you use these as your elementary vortices, A1 to An with curly bracket, with single curly bracket, okay, then the tree level amplitudes computed from this gives you the full loop amplitudes of string theory. Okay, because the loops have already been done and included in the vortex. Okay, so now you only have to calculate tree amplitudes with this. Okay, and we'll also see that this can be used for calculating renormalized mass, for example. Okay, so now I'll have to give another definition. Okay. So we define
Sites occur in 1 pi.
yes, they are still in the same Hilbert space, H hat T and H tilde T.
Don't they have some z?
Some wave function?
Will they differ by some factor?
No, because as far as the action is concerned, I use the same variable, right? Because if we use this particular action, right, and fix Siegel gauge, okay, the tree level amplitudes that you calculate from here will be identical to the full amplitudes that you calculate from the original action, right? So at this stage, I'm not doing any renormalization. When we define the S matrix, okay, then of course the fields that are needed in the S matrix will not be exactly the size, right? They will have a wave function normalization factor, right? At this stage, these are just variables that you use for defining the action. Right? Because the Siegel gauge propagator from here, if you calculate, it's exactly the same Siegel gauge propagator. So when you glue the vortices, right, all that will happen is that you will generate diagrams of this kind. Right? Anything that you had missed earlier will generate back in the Siegel gauge amplitudes of the 1 pi action.
You just corrected the vertices.
Yes.
In 1 pi, we also correct the.
Okay. This one, okay, the sum now runs from 1 to infinity. Okay, because Once you go beyond tree level, right, the 1-point function is not 0 for general string field. 2-point function is non-zero, right? So those will correct the propagators, right? Eventually, when you define the perturbation theory around the shifted vacuum, right, you have to put those in the propagator. Right? Right now, I'm just treating them still perturbatively, right? Because you want to make connection with what we had earlier. Right? But you're right that when you actually try to define a well-defined perturbation theory which doesn't have all the divergences that the usual worldsheet approach has, then we have to correct the propagator, right, by absorbing this into the candidate term. And this we'll do next time. Yeah, if you take the 1 pi effective action and calculate just the tree level amplitudes, that captures the full loop amplitudes of the original string theory. Right? Because each 1 pi vertex contains all the loops, right? So
you will use this
as the action, right? But now with this you are not supposed to do loop calculations anymore. Right? With this you are only supposed to do tree level calculations. Right? You can use the same Siegel gauge and get the result.
But the side to the end contains all loops.
Yes, side to the end by definition is, I mean, first of all, the definition of the curly bracket, original bracket, that itself contains some of the loop contributions, right? Now, this curly bracket contains further loop contributions because you are summing over all possible loop diagrams, right? You are summing over all possible diagrams of this kind. Okay, so let's define a slightly different object, a state. Okay, this in fact can be shown to belong to H tilde t such that so we just define this state by giving its inner product with every state in the dual space. Okay, so once I have defined this, I can also make this also defined. And I'll leave this as an exercise to show that S1 pi is invariant under So there are two sets of gauge invariances. Lambda is in HT, lambda tilde and both are Grassmann odd. So this is a statement that you can easily prove. Okay, that if you do an infinitesimal variation of psi of this form, okay, an infinitesimal variation of psi tilde of this form, you see the lambda is the part which is the interacting part of the gauge transformation, okay, because lambda always involves, this interaction part always involves lambda. Okay. Then you just substitute this in the expression for the 1pi action, and you can show that the 1pi action is invariant under those transformations, provided you use this identity.
Lambda which appears in the first and second equation
Are the same, yes. So lambda which appears in the first and the second equation are the same. This lambda tilde is the distinct one. Right? So this is basically a trivial gauge transformation because this affects psi tilde. Okay, because there is a free field in the theory that's what is responsible for this lambda tilde. It's, yeah, I don't know, it's some kind of surface state. It's like you insert these many different states on the Riemann surface, A1 to N, right? And then you cut out a hole around some other puncture, right? And it's the state that is created at that puncture after you have carried out integration over part of the moduli space of Riemann surface, right? So it's in general a very complicated state that you define. But upon its inner product with any state is well defined because this is a perfectly finite object.
Can I think of it as a particular operator in the OPE of this A1?
Yes, it's basically a product of these, but it's not just OPE because you are putting it on a Riemann surface, right? So also the Riemann surface, I mean, even if there is no operator, right, it will be a non-trivial state, right? Because that's why the 1-point function is non-zero in general. Right? So it's on the sphere, it would be something like an OPE, right? You take the product of operators at different points, and whatever state it generates, it's that.
So it's a state which is prepared by the Euclidean path.
Exactly, by the Euclidean path integral, but it's not just Euclidean path integral, you also integrate over part of the moduli space. Okay? That's the state that you are talking about here. Okay. From the second pointer's viewpoint, this is important because this contains, for example, the diffeomorphism invariance, right? For particular choice of lambda, you can show that that's what generates the general coordinate transformation. Okay? It contains supersymmetry, in, local supersymmetry. Okay, again, for particular choice of lambda in the Raman sector, okay, you generate supersymmetry, local supersymmetry transformation. Okay, so this is the full content of the gauge transformations in the theory. Okay, in this 1pi effective action. Is this clear? Okay, I'll also write down the equations of motion. Okay, so these are very similar to what we had for the BV master action, except that we have this structure, and I mean, from here you can in fact show that one set of fields is free, the other one is interacting. So the way to do that will be that you multiply this one by G, yes, you multiply this one by G, okay, and subtract the first one from there. Okay, this times G minus this, so G times 2 minus 1, so this is 1, this is 2, okay, gives you QB psi plus sum over n, 1 over n factorial, G psi to the n equal to 0. So this is the interacting field equation for psi, okay, psi is the interacting field, okay, and now you can see that given a solution to this, you substitute here to determine psi tilde, okay, and the only freedom that you have in determining psi tilde is to add solutions to free field equations of motion. right? Because two different solutions to this equation for the same psi that satisfies this, okay, is a solution to QB delta psi tilde equal to 0, right? That's the degree of freedom in psi tilde. So that's what shows that the psi tilde gives a free field theory, okay, and psi gives the interacting field theory. Okay. Now from this we can see another interesting point, which is that in general this is not 0. Okay, what does this mean? This means that n equal to 0 term here. Okay, so n equal to 0 term here, right? The definition, well, I have erased the definition. Okay. So by definition phi r C naught minus without anything here, okay, is this. Okay, and in general phi r one-point function of fields is not 0, right? Even if the massless tadpoles are 0, okay, clearly the massive fields will have non-zero tadpole, okay, non-zero one-point function. Okay, so this is not 0, which means that psi equal to 0 is not a solution to this equation, right? You really cannot expand this around psi equal to 0. Okay. So the correct procedure will be to expand around the vacuum expectation value which satisfies the equation of motion. So what we need to do is, so steps, okay, this is what we'll do next time carefully, okay, is to find vacuum solution. Okay, vacuum solution will mean in particular that it should have 0 momentum, right, translation invariant. Okay, it should have 0 momentum, it should be in the NS sector because you shouldn't have a fermionic solution. Okay, so using those constraints you have to find a vacuum solution, okay, that satisfies this equation. Okay. Then we have to expand S1pi around the vacuum solution. Then we diagonalize kinetic term. To find renormalized masses. See, once you have the 1pi action, right, you don't worry about the loops anymore, right? Now you have the full 1pi action, you just diagonalize the kinetic term, that's what will give the full renormalized masses. Okay, no further quantum corrections to masses from there. Okay, everything has already been included. Okay. And finally, we calculate S matrix using LSC. Okay, so this is the basic procedure that one has to follow. Okay, and as I said, next time I'll try to do this in some detail. Yes. A solution, yes. Yeah, that if you set psi equal to 0, the first term is 0. Right? Second term, the n equal to 0 term is non-zero. Right? All the other terms are 0, of course, right? Because they have a factor of psi. So this equation doesn't hold. Yeah, that's what shows the psi equal to 0 is not a solution. You really have to look for a vacuum solution. Right? If there are no massless tadpoles, then finding the vacuum solution is reasonably trivial. But if there are massless tadpoles, then it becomes more complicated. Okay. So in the rest of the lecture today, what we will do, okay, is to give some simplification that is possible. Okay. Because while this procedure works quite well, okay, it's somewhat annoying that you have to deal with infinite number of variables, right? Because this string field theory that I described, as I have said, has infinite number of fields. Okay. So for example, when you say diagonalize kinetic term, right, to find normalized masses, this requires that you have to diagonalize an infinite dimensional matrix. Okay. It is still possible to do it systematically, okay, but you have to still make some effort to determine how to do this. Okay. So it will be much nicer if we could work with a finite dimensional system, right, a finite number of string fields, and that's what I'll try to describe now, how for practical utility we can actually work with finite number of string fields without giving up any of the details of the theory. You will get this is still the exact result, okay, well, exact in perturbative sense. To any order in perturbation theory you can get whatever the full string field theory would have given, okay, but you can get by using a finite dimensional theory.
Additional to double the gauge symmetry, is it related to the double field theory?
It's probably not. No, I don't think it's related to a double field theory as such, right? Because this double field theory is there, for example, even in the bosonic theory, even in the NS sector, right? This is needed just for the Ramond sector. I mean, here I have doubled also the NS sector, but that was not necessary. Because in the NS sector, G is 1, right? Identity. So you could have just set psi tilde equal to psi, right? And gotten just one set of theories. So this doubling is somewhat of a just technical tools to get the correct structure of the action, right? At least I haven't found any further significance of this doubling. Yeah, and it has also the wrong sign kinetic term, right? The psi tilde field has a wrong sign kinetic term, yeah. Maybe there is some connection, but one doesn't know. Okay, so now let me describe some tricks that let us work with a finite number of fields, and that will be the idea of integrating out unwanted fields. So in a given situation, okay, we are interested in calculating some kind of S matrix element, okay, which means that we have a certain set of initial states, okay, and given a certain initial state, okay, we can only produce a certain number of final states. The number of final states that you can produce, right, number of particles that you can produce is finite because you have a certain amount of center of mass energy. Okay. So for example, a very heavy string state you will never produce, right? It's just kinematically impossible to produce very heavy string states. In some cases, it may be impossible to produce certain states just by charge conservation, say. Okay, so in any given scattering process, you expect that only a certain finite set of states will be involved. Okay? And so the idea here will be to see how we can systematically integrate out everything else, okay, and get a theory involving only those finite set of fields, okay, which nevertheless has the full details of string theory. Okay, that we don't want to give up, still want to get the full Venetian amplitude in its correction. Okay, but nevertheless, you want to see how to integrate out those extra fields. So formally we will denote by P. Okay, let's suppose we have a P which is a projection operator. Into a finite subspace of H tilde T and H hat T, okay, that commutes with certain operators. This is technically important, that commutes with QB G L naught plus minus naught plus minus. Okay. So example will be, for example, P projects into states below a fixed mass level. Okay, where mass level basically means that if you take L naught plus, there is a momentum contribution, and then there is some constant, okay, which determines the mass square of the state. So mass level basically refers to this. And so if you project into states below a certain mass level, which has L0 eigenvalue, L0 minus k square by eigenvalue less than some fixed constant c, okay, that projection operators will commute with all of this. Okay, this you can easily check. Okay, because L0 plus commutes with all of this. On the
spectrum in unwanted projecting the heavy state, but project down.
Yes, you can do that. It, I mean, for some reason, if you want to do this, you can do it. As long as P commutes with this, the formalism that I'll be describing will be true, right? But typically, we would like to include in P the massless states, because the massless stat poles otherwise will cause problem. Because as you'll see, we'll try to integrate out all fields other than the P invariant subspace, right? And if you have massless states in the list that you are trying to integrate out, right? And if there are massless stat poles, then of course you'll run into difficulties. Okay, if there are no massless stat poles, then you can do that. You can keep a heavy state and integrate out all the light states in principle. That is, the formalism has no difficulty in extending there in such cases. Okay. Now suppose we take some set of states A1 to An in P H hat T, okay, which means that these states are all P invariant. Okay. We'll define this symbol A1 to An E, okay, this E will stand for effective. Okay, note that I have used the same curly bracket, okay, and the reason will become clear later. Okay, but it's not the same curly bracket as the original curly bracket because I have the subscript E. Okay. So what is this? This by definition is a full Green's function of external states A1 to N computed with propagator okay. So Siegel gauge propagator was B0 plus B0 minus L0 plus inverse G. I just inserted 1 minus P. Okay. Which means that the states that you are summing over in the internal lines, okay, they are outside the P invariant subspace. Okay. They are in the 1 minus P invariant subspace. Okay. And this is clearly the notion of integrating out all fields other than the subset that is contained in P. Is this clear? Okay, so if you take this definition, okay, and if suppose you take this definition, now you use this as a vortex, elementary vortex, okay, and use only P invariant propagators, okay, then you will again get back the full string theory amplitudes, okay, because the contribution from the P non-invariant propagators have already gone into the definition of this vortex. Okay. So you have to just calculate the amplitude using P invariant propagator and these as vortices. External legs are all in the P invariant subspace.
Yeah, but they're not, you don't multiply by the problem. They're not.
No, because you always truncate the external propagators you always remove. Because in the definition of the vortex, you always have external propagators removed, right? So here also, yeah. So the full Green's function, okay, they can external legs truncated. Legs truncated. Okay, now let's ask what is this word identity. Okay, so instead of G, now we are using this amplitude. Okay, the same Green's functions, except that the propagators have this 1 minus P inserted. Okay. So you apply this logic again. Okay. Here, nothing much changes, except that of course G will be replaced by those double curly brackets. Okay. Here, in these two, okay, because these are coming from the propagators, you'll have a 1 minus P inserted in between. Right? And now you can see why it's important that P commutes with all of these, because it shouldn't matter where you put P, right? 1 minus P, you just insert anywhere in this propagator. Okay. So what is the result? The result is that previously the third term cancelled the first term, fourth term cancelled the second term. Okay. Now the cancellation will be incomplete, okay, and the incompleteness will be represented by inserting a P operator inside these two. Right? Because this is 1, okay, minus, you will have a 1 minus P. Right, so effectively we will insert a P. So this, yes. Sorry, no, sorry, QB. Yeah, made a mistake. This is QB. QB hat will come tomorrow. Okay. So this will be given by minus phi r and phi s. This is all E. Oh, there's a P here. Okay, and in fact, because there is a P acting on phi SC, you can also just put a P on these. Okay, it makes no difference, because once you have the projection operator here, you can also insert the same projection operator here and here and here. Is this clear? Because once phi SC is P projected, then its dual is also P projected by definition. So this now looks like the same identity that was satisfied by the original double curly bracket without the C. Yeah, that was original what? Okay. Except that now all the external states are in P invariant subspace, and the basis states over which you are summing are also in the P invariant subspace. Okay? So now we can write down an effective action Yes. Let's see, if we take the original identity, see, it's not the P projected identity from the original identity, because in the original identity, right, in the intermediate states, you summed over everything, right? So if you just make the external states P invariant, right, you don't get still that identity, right? Because the difference here is that here in the internal lines, we are only allowing P invariant states to propagate, right? And because of this, what changes here is that this is where the propagator information is, right? And this is where you inserted extra 1 minus P. Okay? And that's what gives us to this P projected things on the right hand side. Right? So, yeah, because this certainly is, this vortex, this effective vortex is not just the original vortex restricted to P invariant subspace. Okay, that you can see, because suppose you take the original vortex, okay, and restrict to P invariant subspace. Okay. The identity, these will be small a, right, but these sums will still run over the full Hilbert space, right? That you cannot restrict to P invariant subspace, right? But once you define these new curly brackets, right, by summing over all the P in non-invariant intermediate states, right? Now you have got a new identity which looks similar to the original identity. Okay. But now both the external states are P invariant subspace, and the states that we are summing over in the intermediate state, those are also in P invariant subspace. Right? So you really need to integrate out the P non-invariant states. Okay, so now suppose define string field we introduced string field phi tilde in P H tilde T and phi in P H hat T. Then if we write down the effective action as 1 over GS square, this satisfies the BV master equation. Okay, and the analysis, okay, which I didn't do, of course, okay, that this satisfies BV master equation as a consequence of these identities, okay, is exactly identical to why the original action satisfies BV master equation in terms of original identities, because the identities are identical, right? Everywhere, all that has changed is that the double curly bracket has been replaced by the effective double curly bracket, okay, and all states, okay, external and internal, have been replaced, have been forced to be in the P invariant subspace. And if you take this action and now fix the Siegel gauge, okay, and calculate Feynman amplitudes, okay, you are guaranteed that these Feynman amplitudes, where now we have a finite set of states propagating, right, because P invariant subspace by definition you have chosen to be a finite dimensional subspace. Okay. So this is a field theory of a finite dimensional, finite number of variables, finite number of fields. Okay. Nevertheless, the amplitudes calculated from this string theory, this field theory, gives the exact string amplitudes. Okay, you have not lost any information, okay, as long as the external states are restricted to the P invariant subspace. Okay, what you have lost is information about amplitudes where the external states are outside the P invariant subspace. Okay. But as far as external states, P invariant external states are concerned, this contains the full information. Is this clear? So this is in some sense an answer to Suvlot's question that in principle, if you want to work up to for a given problem, okay, with a given amount of center of mass energy, Okay? You can always choose to work in a finite dimensional field theory. Okay, field theory is finite number of variables without losing any of the information of string theory, at least perturbatively. And you can in fact go ahead from here and do what we did for the full action. In particular, you can define the 1pi effective action from here. Right? You take this, now you integrate out all the you sum over all the 1pi amplitudes computed from this, and that will give the 1pi effective action of these p invariant fields. Okay? And that will have exactly the same structure that we had described earlier. Okay? So what we'll be doing next time, okay, is that we use this 1pi action to go ahead and see how to do mass renormalization and massless tadpoles and so on. Okay? But you should keep in mind that whatever I'll do, okay, even though I'll do in the context of full string field theory, okay, that can in principle be done for a theory of this kind, okay, because analysis is identical, okay, and the advantage of working with a theory of this kind is that you never have to worry about infinite dimensional fields. Okay, you can always use a finite dimensional field space without giving up any of the details.
But it's a little confusing because this seems a little different from usual effective field theory, where you cut the momentum also.
Yes, okay. So I was coming to that. Okay, that is the last part that I want to discuss, but I don't have the enough technology to discuss it fully here. Okay, but let me just say what happens. So a special case of this, okay, will be restrict to massless levels. Okay, so suppose P is the projection operator to massless states. Okay, at least states which are massless at tree level. Okay. Then you have integrated all the massive modes. Okay. Now this is partly what to do in deriving Wilsonian effective action. Okay, you first integrate all the massive modes. Okay, but in Wilsonian effective action you do also something else, which is that you integrate out all the high energy modes of the massless fields. Okay. So the question is there a sense in which this effective action that you have given here, okay, also integrate out the high energy modes of the massive fields, of the massless fields. Okay. And what one can show, okay, is that in string field theory, as I have been emphasizing, the string field theory that we are writing down is not unique, okay, because you have the choice of section, okay, this R bar GMN that we chose, right, that depends on a choice of local coordinates, the picture changing operators and so on. Okay. So there is a choice in how to choose in this R bar GMN, okay, and in particular there is a parameter inside R bar in the choice of R bar GMN, okay, which is normally called the stub length. Okay. And the role of this parameter is that by adjusting the parameter you can ensure that all the high energy modes are integrated out. Okay, that parameter as you vary, okay, in one extreme limit of the parameter, effectively you have integrated out all the high energy modes. Okay. So in that sense, you can regard this as a Wilsonian effective action, okay, where that parameter plays the role of the cutoff. Okay, the UV cutoff. So basically that parameter will appear as the UV cutoff of this theory. Okay. So let me roughly indicate how that goes. Okay, now I think I can erase this. I don't need this anymore. So suppose you have a field theory based on this and you have Feynman diagrams, okay, you have this, you have this and many other Feynman diagrams. Now what you want for going to the infrared, suppose you want to integrate all the high energy modes, okay, then what you want is that contribution from, most of the contribution from these diagrams, okay, should be going into the definition of the vortex, right? If you want to integrate out high energy modes, right? Typically there is momentum modes flowing here, okay? What is the meaning of integrating out the high energy modes? Okay, that the high momentum modes, mode contribution here should go into the definition of the 4-point vortex, okay? And only the very low momentum modes should be allowed to flow in the loop. Okay, so let's see how that can be achieved. Okay, in the language that we describe. Okay, so if take any particular vortex in this Feynman diagram. Okay, the elementary vortex, say 4-point vortex, or first take a 3-point vortex. Suppose you could multiply this 3-point vortex, okay, by a contribution of the form exponential minus c. Okay, you are considering mi equal to 0, but let's consider the general case. Okay. Suppose there is a way that you could multiply this amplitude by a factor like this for some positive constant c. Okay. Then what is the effect of this c? You see, when external legs are on shell, it makes no difference. Okay, it doesn't affect the amplitude. Okay. But when the external legs try to go off shell, okay, it suppresses the amplitude. Okay, is this clear? So if you multiply the vortex by this and substitute in this off shell amplitude, okay, it will suppress contributions where the loop momenta are large. The loop momenta which are running are large, okay, large and Euclidean. Okay, in fact that's the reason why I cannot explain it fully. Okay, because as we know, perturbation theory, the loop momentum integral are not Euclidean, so this doesn't have a fixed sign. Okay, but there is a way to reorganize the perturbation theory where you can think of this as Euclidean momenta. So let's accept that for now. Suppose there is a Euclidean momenta. Okay, then large Euclidean momenta flowing in the loop is suppressed. Okay, so this will achieve this. So effectively, you are increasing C means that you are basically bringing down the UV cutoff of the theory. Okay, any high momentum modes are highly suppressed because they cannot flow in the loop. Okay, but of course, you don't want to change the theory. Right? You just don't want to change the result of this amplitude, this contribution, without dumping it somewhere else. Okay, and you want to dump it to the 4-point function. Okay. And what we'll see now is that that happens automatically in the context of string field theory. So let's see how this is done, how this is achieved. Okay, how is it possible to multiply the vortex by a factor like this? Okay. So for this, recall that for this vortex, right, you will define a sphere 3-point function. Okay. But because there are off-shell external states, you will have to choose local coordinates at the punctures. Okay, also PCO locations, but for our purpose, the local coordinates at the punctures are important. Okay. So suppose WA for A equal to 1, 2, 3, these were the initial choice of local coordinates. Okay. And we define some W tilde, which is WA over lambda. Okay, where and you take the limit, okay, to take this W tilde equal to W over lambda. You can check that the effect of this, okay, is that it multiplies, if you change local coordinates from WA to W tilde, okay, it multiplies the 3-point function by mod lambda to the power h plus h bar. Okay, where h and h bar are the conformal weights of these operators. Okay, whatever vortex operators are inserted here. Okay. For on-shell states, h and h bar are 0. Okay, so it makes no difference. Of course, which should be true because on-shell amplitude shouldn't depend on choice of local coordinates. Okay. But for off-shell states, okay, as the conformal dimension goes up, for sufficiently small lambda, it suppresses the amplitude. Okay, and that's what is captured by this factor over here. Okay. The off-shell amplitudes, the off-shell contribution is suppressed. Okay. But now the question is where is the contribution going? Right? If the off-shell amplitudes are suppressed, okay, for example, this diagram will now capture, okay, a contribution only when this momentum that is flowing here is close to on-shell. Right? If it's large and Euclidean, okay, it will suppress this diagram. Okay. But that contribution, okay, in fact has to go to the definition of the elementary 4-point function. Okay. And the way to see this is that if you now glue, suppose we want to Suppose you take this diagram. Okay. This corresponds to this in the Riemann surface picture. Okay. You take 3 punctured spheres and then do a plumbing fixture. Right? This is W1, this is W2, and you glue by W1, W2 equal to e to the minus s plus I theta. Okay. Now suppose you replace W by W1 tilde, W tilde. So if you take W1 tilde, W2 tilde equal to e to the minus s plus I theta. Okay, this will be the new gluing condition. But this means that in W coordinate, the gluing rule is W1, W2 is equal to lambda square e to the minus s plus I theta. Okay, in the original W coordinate, because of this relation that he had there. Okay. So for small lambda, we see that even for s equal to 0, okay, for s equal to infinity, of course, you are going towards the boundary. Okay. But even for s equal to 0, W1, W2 is very small. Okay. Which means that this diagram, okay, which is obtained by plumbing fixture of these two, okay, is covering a region of the moduli space very close to the boundary. Right? Because in the W1, W2 coordinate system, it's lambda going to 0 means that you are gluing two Riemann surfaces, both of which are very small size circle, and that's what you are gluing, right? So you are already close to degeneration. Okay? So the whole diagram is representing the contribution close to degeneration. Okay? Most of the contribution, most of the moduli space is in fact now coming from the elementary 4-point vortex. Okay? So this lambda parameter is what is called the stub length. Okay? By decreasing the lambda parameter, okay, what you are doing is that you are ensuring that most of the contribution to the amplitudes come from the elementary vortex to any amplitude. Okay. The actual Feynman diagrams, okay, which are propagators, okay, only capture contribution very close to the moduli, to the boundary of the moduli space. Okay. And that means that they capture contribution only from the far infrared region, right? Because near the boundary of the moduli space, okay, all off-shell contributions are highly suppressed, okay, precisely because of this lambda to the h plus h bar factor, okay, and all the contribution is being dumped into a single vortex, right? And that's precisely the notion of Wilsonian effective action, that you effectively integrate out all the massive, we have already integrated out the massive modes explicitly, but you also effectively integrate out all the high energy modes. Okay, we have not done it explicitly, but this lambda parameter achieves that. Okay, and integrate all the high energy modes or high Euclidean energy modes, and only the very light modes, okay, actually propagate in the loop. Right? So it's in this sense that this effective action also can be thought of as a Wilsonian effective action, okay, but that's only if P is something that projects onto, only onto, into the massless states. Okay, it's called stub because there is, another description instead of using the W coordinate, right? If you use this log W, right? Then it's like log the relation between log W and log W tilde is like log W minus log lambda. Okay, so there you have gone to from the plane to the cylinder picture, right? And it's as if you are adding a length minus log lambda, okay, in the external states, right? It's as if you are adding these vortices, okay, that you are gluing these onto the sphere, okay, by adding some cylinders of certain length into the vortices, right? This is in the logarithmic picture. So that's why it's called stubs, right? You are basically in this picture you have already, the vortices already have the stubs attached, right? And then the effect of the propagator is that you attach a cylinder whose length varies from 0 to infinity, right? And then you attach another 3-point function with these stubs, right? And the idea is that if these stubs themselves are very long length, large length, then doesn't matter, even if when the propagator cylinder is going to 0, right, you are very close to the degeneration.
Dependence on this lambda can be used to get the beta function.
Yes, I think in the low energy you can use the dependence on the lambda to get the beta function. You should be able to get, because it's really largely low, right? And effectively you can see that this the field theory that we described, right, has automatically comes with an UV cutoff, right, because all vortices have this exponential suppression factor. Okay, so not only you have a field theory of a finite number of fields, okay, it's a UV finite field theory. Okay, because all vortices have this suppression. Okay, so it's a non-local field theory, right? But this is the amplitudes computed from this gives the full string field theory amplitudes. Right? It's non-local, but it has derivative expansion. Right? There is no difficulty in expanding it out in derivatives. So in that sense, it doesn't have a 1 over k square kind of term in the action. Just exponential, and by the fact that you have integrated out the heavy modes, right? It will also have 1 over k square plus c kind of terms in the vortices. Right? But you never go, k square never approaches c because you have only integrated out those modes which you can never produce. Yeah, if you don't integrate out the massless mode, then you don't, this is non-local, but it has derivative expansion. Yeah, I think in non-commutative theory, sometimes you can get these exponential suppression factors. Yeah. I don't think that is a worry here because here the IR divergences are the regular IR divergences. I don't think you can get any additional IR divergence that you don't already see in quantum field theories. Right? Because the IR divergences are just the s goes to infinity limit. See, the point is that even though we have added these stubs, right, as long as the stubs are of finite length, each vortex is still finite. Right? You go close to degeneration, but you never reach degeneration. Right? So each vortex is still finite. Okay? And the only divergences are coming from the propagators, going to the S parameter going to infinite values. And those are the usual IR divergences, right, which you can handle by the standard field theory techniques. And that probably has to do with the fact that this theory didn't have a UV divergence to begin with. Right? It's just the string field theory is just a way of rewriting original string theory, the string worldsheet theory, which doesn't have UV divergence. So as far as UV divergence is concerned, you don't really need string field theory. I mean, this is needed only to tackle the IR problems. And those are the standard ones in quantum field theories.
But this action won't be unitary.
It will be unitary in the sense that it will be real as long as the momenta are below the threshold, right? And because we have already chosen we have chosen to integrate out fields which you cannot produce in a given process. Okay? That's why I said that if you are looking at a given S matrix, right, then you have a certain amount of external center of mass energy, and you integrate out only those fields which you can never produce with that center of mass energy, right? So the vortices that will appear, right, the kind of momentum that will appear in the vortices are all of the kind which do not cross the threshold, right? And in that range, these are perfectly real vortices.
But in the intermediate states, if you don't suppress the loop momenta.
Yes, you don't, but you do suppress loop momenta. So
you suppress loop momenta if you adjust parameter.
Yeah, but even if you don't adjust this parameter, right, for any sensible choice of vortices, you can show that there is always an exponential suppression factor, and that has to do with the UV finiteness of string theory. Okay? But the point is that you could still worry that in the loop momentum, right, if you had taken the energy integrals to be along the real axis, okay, then by taking sufficiently large energy, loop energy, you can cross the threshold. Right? That we'll discuss near the end, that the way to do the loop integral is not to do the energy integral on the real axis, but you have to turn the contours, right? And there you have to find the spread, so the energy integral, the loop energy integrals will actually start from minus I infinity and go to plus I infinity, right? In the interior it will spread along the real direction, okay? But the spread that you have typically is of the order of the center of mass energy of that is available in the given scattering problem, right? So you never reach the poles, right, which you have integrated out, right, provided your center of mass energy doesn't allow you to produce those particles. So in that sense, you can pretend as if the vortices are real, even though you know that if we take the momentum to be sufficiently large, energy to be sufficiently large, then you get imaginary part. from integrating out these massive bonds.
So it's unitary within a center of mass energy.
Exactly. So for a fixed center of mass energy, if you integrate out the fields which are beyond that, then the relevant part of the vortex that you need for computing S matrix is real, right? And so in that sense, it's unitary. Okay, so next time then we'll discuss how to find a vacuum solution, okay, or more importantly, how to expand the action around the new vacuum solution and carry out the master normalization and other aspects.